Dee and Clark said I shouldn't do this video in this way, that no one would get the reference, but I have 126 or so followers on YouTube, so I think I know what I'm doing. Anyways, I'm about to make the most Canadian reference I possibly could and just say, you know where the puck is on the end of your stick. And some people will not get the reference, but basically, in hockey, you have a puck. That's the thing you hit. You know, it would be like a soccer ball in soccer or a football in football. I don't know what we're talking about there. But anyways, when it comes to this, when it comes to the location of the puck, it doesn't really matter who you are. If I put it somewhere on the stick and you close your eyes, you're not even looking at it, newbie or pro player, and you go to move that stick, hit that puck, you can tell where it is. It could be in the back, more on the heel of the stick, or more on the front of the stick. And with more and more experience, you know more and more precisely where you're holding it. So as you do stick handling, as you move it back and forth like that, you start to understand better and better, but essentially pretty quickly where that puck is located. And that's important to know because it makes you able to control where it's going, and it's all about where it's going. So how does that work, and why is that relevant too? Understand that as you try and hit, as you come in and you try and actually move that puck, you come in with a big movement of your stick, the puck will be pushing back on the stick. It will resist the movement of that stick even just a little bit. If we go to a top-down view, so this is the blade of the stick and this is the part you're holding here. I've removed the tape for convenience's sake, so we're looking at it from the top down. Let's assume that the hockey puck is a little more to the front here. And it doesn't really matter where, we can talk about it in either location. So as you go to bring the stick this way against the puck will push back just slightly. We're not talking about much here. We're not talking about a ton of force, but as that stick pushes on the puck and the puck resists, based on the leverage all the way up, all that leverage coming up the stick, it will push the stick into a rotation like that. It'll be around a vertical axis, and so it means that that stick will resist, it will twist when we have that puck more on the distal end, if you will. So if it's here, it makes it rotate. So based on our real high-tech analysis, watch this. Oh, amazing, right? Totally amazing. Okay, now we could say another thing. Let's talk about this. Let's go back to our first view. So if that puck happens to be more on the front, just understand that force will resist the motion, and it will travel up, and then we get a rotation of the stick. Real simple. The further out it is, the more we get a rotation based on the shape of that stick. However, if we then have the puck more at the heel of the stick, more here, or here in this case, you're going to see that instead of rotating, instead of doing this because it's long lever, what it will actually do is push more straight to the side, or resist straight to the side as the stick comes this way. So just like before, if we look at the long part, if the stick is coming this way, it will simply push straight back. And so we won't feel a rotation. We won't have this, but instead we will just have the stick move a little bit, or resist, more so resist in the opposite plane of direction. It'll take a little more force to push that puck. And all that means is that we can better understand, based on the movement of the stick, without even physically looking at the puck, we can tell where it is on our stick. We can tell why we would want to push it in a certain direction. We can tell how we're going to do that. And there's no sight. We have no eye line on it. This is what athletes do all the time, and you get better and better as you go. But even a novice can do that to some extent. So that's really cool, for one, especially if you like hockey, but it's also really useful. So if I tell you you can do that, if I say that, tell someone, oh yes, you can feel where the puck is, nobody bats an eye. Everybody goes, yep, that sounds fine, especially if you're Canadian. But if I instead tell you that you can use the foot to tell what the leg is doing, then people do one of two things. They either think you're crazy, or they think you're lying, or they think you have magic powers, and hopefully neither case is true. In any case, this is a good example of how long leverage works, because it can go both and it can go both ways. If the leg is moving, and we'll just get rid of these guys here for a second, if the leg is a moving leg, it's doing flexion, extension, whatever you want, rotation, something to that effect, it will transfer that force all the way down the leg and into the foot. That's how that works. One side will pull on the other and vice versa. However, oppositely, if we switch this up, like in our last video, this is a continuation of that. If we internally rotate the foot well, it becomes a functional unit. It cinches up the attachments between. It cinches them up, reduces their length to the point, or it actually increases their length, reduces their flexibility to the point at which the forces of one are instantly transferred into the other. So one to the other, essentially right away. So this means that by internally rotating that foot and then pulling on it backwards and forwards, I actually get an idea of what the hip is doing without touching it. I might even get an idea what the pelvis is doing higher up. This is long leverage, and this is actually palpation in a way through long leverage. And this is normal. Again, it is hard to understand unless you can do it, unless you can feel it, but that is essentially how it works. It's the exact same thing as knowing where the puck is based on your stick. It's just that through the leg, by the way the leg resists motion, if it doesn't want to go this way, for instance, it's probably stuck somewhere up here, or vice versa. Knowing the way the foot moves will tell you, knowing the way the foot and the whole leg moves will tell you something about how the pelvis all moves as a functional unit now. Okay. Now, side note, would it not be pretty cool if you could see a game of hockey played with bones for sticks? You know, morbid, agreeably. You know, that would be disgusting. But, I mean, pretty cool. Like, how much would you pay to see that? Would you pay, like, you know, $300? $400 a game to see that? Well, guess what? That's what tickets cost anyway, so the least they could do is use femurs. If you spend a lot of time there, and maybe you make, you know, you pay, I don't know, $100,000 worth of tickets, food, concessions, you may actually one time, if you're very, very, very lucky, you might see the Leafs win. Okay, second point. Understand that the hockey stick is a very good example of how this leverage works almost instantaneously. So if that puck, wherever it happens to be, is on the stick, now when we're talking about carbon fiber now, of course, so there's a little bit of a torque, there's a little bit of a bend, and those slap shots are amazing, but there's a little bit of a bend and a torque. The transference from one, when you're holding the stick, to the other, to the distal end, is near instantaneous, a small bit of a lag. So when I move the top of the stick, it's understandable that the bottom of the stick will move a proportionate amount. Relative to the lever you've created, of course, if you have your hands higher and lower, if you shift a hand down, it's going to move differently because the axis changes, so maybe it's from here versus here. But it means that there's no loss of force in between. And this should be true of the leg as well. You should see it when you're generating long levers in the human body. So, as you internally rotate that foot, like we were talking about in the last video, if you've done it well, if, say, you know, your adductors, you've taken up the slack in them, if the rectus femoris is, you know, working quite well for you, if your gastroc muscles are the slack's been reduced and they're nicely transferring the forces, it should be that the movement here in the foot, flexion, extension, side bending, rotation, goes straight into that target area, whether it's the innominate, the pelvis, the low back. There should be no loss of force. When you move that leg through the foot, you should see it show up in the pelvis, and you should feel it show up in the pelvis. Now, the big difference between a human leg and a hockey stick is the hockey stick has no joints. And again, though it is made of carbon fiber or traditionally wood, there's a bit of give to it. But you don't have that same thing in the leg. There's lots of joints along the way. Each one of these, just the joints. So if we just take the joints, has a fluid Layers, okay, each one of these has a fluid component to it. They have a synovial fluid, multiple synovial fluids, and as well a ligamentous structure surrounding it, whether that's, capsule, hip ligaments, stuff like that, MCL, LCL, ACL, all that. They all have a ton of ligaments around it. And then, of course, all of the muscles we just talked about, all the muscles we just added in, and that's only a few of them. Understand that each one of these soft tissue structures can create a distracting or offsetting force. You may be aiming for something, but should there be a fault in any one of these tissues, whether it's too tight or it's too lax, it will send your leverage off center and you will end up missing the mark, which is telling you something about the fascia, telling you something about how it's being held together or not being held together. And that's something we have to deal with when we're talking about manual therapy. Anyways, I hope that made sense. This has been Elge from Simple Lines Anatomy. Simple Lines Anatomy, where we believe our athletes look better with less teeth.